Hello everyone, my name is Federico Palazzetti and I will talk about total integral cross-sections and potential energy surfaces from molecular beam scattering experiments on propylene oxide helium and propylene oxide neon. The work has been done in collaboration with Cecilia Coletti and Fernando Pirani. The information provided by this work is crucial to evaluate the spectroscopic features and dynamical selectivity of weakly bound complexes formed by propylene oxide by collisions in interstellar clouds and winds in the space and planetary atmospheres. In particular, the interactions of propylene oxide with helium and neon have been studied for the first time in the gas phase by molecular beam techniques. The total integral cross-sections have been measured as a function of the selected collision velocity under high angular and velocity resolution conditions. It permits to obtain resolved quantum Glory interference effects and provides information on the absolute scale on the long-range attraction and on the average binding energy in the range of equilibrium distances. The experimental results, combined with a theoretical phenomenological approach, have been used to derive and test the potential energy surfaces. These potential energy surfaces, defined in the full space of relative configurations, can be implemented in molecular dynamic simulation codes. Their formulation can be extended to more complex systems. This is the structure of propylene oxide. It attracted interest from astrochemists after it was detected in interstellar cloud Sagittarius B2. Experiments have been carried out in the gas phase with the molecular beam technique. High-resolution single collision conditions are realized useful to measure the velocity dependence of the total integral cross-section. The measured cross-sections are plotted as a function of the velocity to 2 out of 5 to emphasize the Glory quantum interference, which appears to exhibit a small amplitude in both cases. Moreover, the helium-neon propylene oxide systems exhibit completely different behavior of the observables, thus revealing significant variations in the intermolecular interactions which drive the dynamics of single collision events. A pairwise additivity approach has been adopted to provide an analytical formulation of the intermolecular potential. The total interaction has been defined as a sum of improved Lennard-Jones potential pair contributions, each one involving the noble gas atom and one of the 7 centers distributed in the propylene oxide molecular frame. We selected as most representative propylene oxide interaction centers the asymmetric carbon, the carbon of the CH2, the 3 hydrogen atom of CH and CH2, the oxygen atom, and the methyl group, which is considered a structureless partner. For each interacting pair, the improved Lennard-Jones contribution is expressed by this equation, where R is the distance between the rare gas atom and the individual center of the molecule. Epsilon and Rm are respectively the potential wear depth and the equilibrium distance associated to the considered pair, while R out of Rm is the reduced distance. For neutral pairs, the parameter m is 6, while beta is a parameter related to the hardness of the two interacting species, and for the present system, its value is comprised between 7.5 and 8.5. The potential energy surface is a function of the spherical coordinates r, theta, and phi. Here we report the contour maps of helium propylene oxide potential energy surface at the distance of 4 angstrom and 3.6 angstrom. The minimum energy path is traced by a red dashed line on the contour maps, while in the right we report its profile. It suggests that while phi can range from 0 to 360 degrees, the variation interval of theta is much more limited by repulsive contribution. The minimum energy path provides some information on the possible most stable configurations assumed by the system at each selected distance, suggested by the comparison between the height of energy barriers that hinder the revolution of helium around the propylene oxide molecule and the available molecular rotation energy RT that promotes this revolution. The minimum energy path at 3.6 angstrom shows the 3 barriers whose height is of the order of 4 or 5 millielectron volt, thus much lower than RT that at 300 Kelvin amounts to 25 millielectron volts. Here we report the contour maps also for the neon propylene oxide at 4 angstrom and 3.7 angstrom. The most evident difference with respect to the helium propylene oxide potential energy surface is given as expected by the larger height of the barriers. We have found 5 minima in the potential energy surface of propylene oxide and helium. For each minimum, we report the values of the angles of theta and phi, the distance of equilibrium, and the watt depth. For each of these values, we report the results obtained by our model, by reference data based on ab initio calculations, and ab initio calculations performed by us and based on complete basis set as a combination of MP2 and coupled cluster methods. Here we also report the configuration of a global minimum. Concluding, the method adopted represents the intermolecular potential by an analytic formulation that makes use of a few parameters with a well-defined physical meaning. From the topography of the potential energy surface, it is possible to evaluate the minimum energy path, which is a basic information to define the easiness of adiabatic transition between different configurations of the interacting systems. The most stable configuration at long range can substantially differ from that in the region of equilibrium distance. The formulation of the potential energy surface for heavier rare gas atom, as well as for more complex systems, can be obtained by scaling the potential energy parameters for the different polarizabilities. These potential energy surfaces are necessary to evaluate and investigate possible collision alignment processes. The analytical formulation of the potential energy surface allows the calculation of physical, dynamical, and spectroscopic properties of the systems, which selectively depend on the weak anisotropic forces both at long and intermediate range of separation distances. As a general conclusion, the proposed methods can be considered basic for addressing theoretical investigation toward the configurations proper for the search of minima in multidimensional surfaces of increasing complexity. I conclude by acknowledging the Italian Ministry of University and Research for financial support and all of you for your attention.